So we learned about the operation of differentiation in the last lecture. Let's take a quick recap about that. So we saw that if we have a function y being the function of x, so x is the independent variable and y is the dependent variable, then the instantaneous rate of change of y with respect to x is given by the operation of differentiation conducted on the function fx. So this is the instantaneous rate of change. And this comes by differentiation of the function fx. Okay. Now we had seen the operation of differentiation, the basic formula for differentiation. That differentiation of x to the power n is given by n into x to the power n minus 1. Okay. And also differentiation of any constant is equal to 0. All right, and then we had seen the couple of properties of differentiation. That if we are differentiating a constant multiplied by a function, and that becomes the constant times differentiation of the function. And if we are differentiating the sum or difference of two functions, that becomes the sum or difference of their individual differentiations. Okay, so these are the essential things that we learned in the last lecture in terms of differentiation. Okay. We've also discussed, of course, a number of things, that the geometrical interpretation of the differentiation is that it gives us slope of tangent, or instantaneous rate of change gives us slope of tangent, whereas average rate of change gives us slope of secant line, etc., etc. Okay. But let's focus on this part right now. So I want to discuss few of the questions which I had given in the assignment last time. Even though I have given you, I have sent you detailed solutions or hints along with the answer key. Okay. But just to reiterate the application of these principles which I've listed out here, let's look at few of the questions. So let's look at C part of question 1. Y is given to us in this as cube root of x, and we want to find
power 1/3
dy by dx. Yes, you have some doubt, beta?
No, sir, x to the power 1 by 3.
Yeah, very good. So we will express this as x to the power 1 by 3. Okay, before I continue, there are a couple of questions on the text which I have received. So let me explain them. Okay. So Tanya is asking, does it have any particular unit? Yeah, rate of change will have a unit when we express it in terms of physics. Okay. So see, in terms of maths, if we are expressing y as a function of x, where x and y are numbers. Okay. So essentially they are unitless. Then dy by dx is also unitless. Okay. But if we apply, when this is applied to physics, okay, x will be a variable with a unit, and so will y. Y will be the dependent variable with a unit. So accordingly, dy by dx, it's by definition, it is what? It is limit delta x tending to 0, delta y by delta x. So this will have the unit of y divided by the unit of x. Okay, then I understood this point. Because it is a change in y divided by change in x. No? Very small change, but all the same, it's a change in y. So for example, if we are expressing distance as a function of time, then instantaneous speed is defined as rate of change of distance with respect to time. So if s is in meters and t in seconds, then ds by dt will be in meters per second. Okay, simple example you can remember of this. This is the most direct and common application of differentiation. Okay, so hope this is clear. Okay, and Ruchi, we will come to question number 4e also. Okay, now Parth has asked why differentiation of a constant is 0. The answer to that, you can see it lies here only. Okay, it is change in y upon change in x. No? So if you look at the constant function, if y is a constant, then how the graph of y versus x looks? It looks like a horizontal straight line.
Yes, sir.
So the slope of it is 0, no? Okay. So delta y by delta x for this line is 0. So dy by dx will also be 0, because dy by dx is delta y by delta x, but under the limit that delta x is very small, or it is the slope of the tangent at any point. So the slope of the tangent is the same as the slope of the line, right? So hope this point is clear, Bharat?
Yes, sir.
Okay. Okay, so let's continue ahead with this example. So as we were saying, that to differentiate this, we have to operate differentiation on cube root of x, which we can express as x to the power 1 by 3. And then we can just use that formula for differentiation of x to the power n is nx to the power n minus 1. So just replace n with 3. So this becomes this. So we can leave the answer this way also, or we can simplify it further and write it as this. Okay. or simplify it further, we can even write it as cube root of x square. Okay. So all these answers are correct. Whichever form you leave it in, it's fine. Okay. So this is a direct example of the application of this formula. Okay. Now next, let's look at an example with the application of the properties also. Okay. So let's look at part F of question 1. So y is equal to x cube minus 2x plus 6. So in this, we will use a combination of the properties that we had discussed. Okay. So when we differentiate this, you can see that there are a number of terms inside. Okay. So next, as we simplify, as we open this bracket, we can write it as the differentiation operator on this term minus the differentiation operator on this term plus the differentiation operator on this term. Okay. So this will directly become 3x square. Here the 2 can come outside. Okay. And differentiation of a constant is anyway 0. Okay. So this becomes our answer. Okay. So hope these two examples are clear to all of you.
Yes.
Yeah. Just minimize it, go through it once. Okay, anybody has a doubt in the second question?
No, sir.
Yeah, you have a doubt in the second question?
No, sir.
Yes, sir, in the third part.
Okay, let's understand. Okay, so in second question, it's like the scenario of a drag race kind of thing. Now, two objects are starting from the same position along parallel straight lines. They are both starting at time t equal to 0, but they obviously have different patterns of motion in terms of velocity, acceleration, etc. Okay, so therefore their displacements are expressed as different things. So at t equal to 0, both of them are starting from here, such that as A moves along this line and B moves along this line, at some time t, the distance traveled by A, or you can say the displacement also, because it's along a straight line, is given by this function, right? And the distance traveled by B is given by this function. Okay. So now let's understand what information we can get from this. Okay. One is we can compare where they are at different points of time. The other is we can also get from this that the instantaneous velocity of A will be the rate of change of displacement with respect to time. So A's velocity is differentiation of 8t square with respect to time. So that is 16t. And B's velocity, similarly, is differentiation of B's displacement with respect to time. So we can also get the information about their individual velocities as function of time. So these are distances or displacements as function of time. So now, for example, if we compare from this information, if we compare at t equal to 1 second, what are their displacements? This one is 8 meters. This one is 4 meters. Okay. So that means A is ahead of B. Okay. And the velocities, this is 16 meters per second, and this is 12 meters per second. So you can also see that A is faster. So if we compare this at, for example, t equal to 1 second, we can see that A is ahead, B is behind, and also A is faster, B is slower. Okay. Now let's compare this situation to what is happening at t equal to 2 seconds. So A is at 32 meters. B incidentally is also at 32 meters. You're getting from this formula. Just substitute t as 2 seconds. So that means they are alongside. Okay. And at this point of time, if you check what their velocities are, you'll realize that B's velocity has become more than A's. Okay. So by the time you're at t equal to 2 seconds, B has caught up with A. They're alongside, and B's velocity is also more than A's. So what you'll realize is in between 1 and 2 seconds somewhere, B's velocity has become more than A's, because that's the only way B can catch up with A. Okay, and to confirm that, you can also check, for example, that at t equal to 3 seconds, expectedly something like this should happen. A should be behind, and B should have moved ahead by then. Okay, that you can check, because at 3 seconds you can see A's displacement would be 8 into 9, 72 meters, but B's displacement would be 4 into 27, so that's 104 meters. 108 meters. Yes. What is the doubt? Whereas their velocities at 3 seconds are 16 into 3, that is 48 meters per second for A, but B's is much more. You can see it is 12 into 9, that's 108 meters per second.
Sir,
Yes.
sir, in the C question 2C, you have
Yes.
given that at what point of time does B overtake A?
Yeah.
So, sir, it should be 3 seconds, no? Because the
No.
distance of B is more than distance of A.
But what about at 2.1 seconds? तभी तो ज्यादा हो जाएगा ना?
Yes, sir.
So overtake actually कब कर रहा है? At this instant of 2 seconds only, na?
Yes, sir.
So if I want to find when does P overtake A. So for B to overtake A, the condition is that the displacement of B should become greater than equal to the displacement of A. At the instant when it becomes equal to, that's when it starts to overtake. What's the point now?
Yes, sir.
So the
And sir,
condition
in
for this
E-
is that 4t cube should become greater than equal to 8t square. So this is what we have to solve. And when we solve this, we'll see that this is for t greater than equal to 2 seconds. Okay. So you can see that this will happen moment t is greater than equal to 2 seconds. So that means B overtakes A at t equal to 2 seconds itself. Okay. So that's how we solve the C part of the question. Hope this is clear.
Yes, sir.
Okay. And similarly in the D part, you're asked to solve when does B become faster than A
Sir, B becomes faster than A at 2 seconds, no?
No, because you can see that if that was the case, then at 2 seconds, B would have been behind A, because up to 2 seconds, A would have been moving faster. So B
Yeah.
must have increased its speed more than A speed, somewhere between 1 and 2 only. Because at 1 second, B was behind, and at 2 seconds, B has caught up now.
Yes, sir.
Okay. So what is the condition for one object to be faster than the other? Its instantaneous velocity must be greater than, if we are saying faster, then it must be greater than A's. So the instantaneous velocities are given by this 12t square. This should be greater than 16t. So same method of solving, but just the values are different. So here we can take 4t. So t should be greater than 4/3 seconds or 1.33 seconds. So the moment when B speed actually becomes greater than A is exactly that moment 4/3, because after that you can see the velocities become more. So up to 4/3 seconds, A is moving faster than B. So the distance between them is increasing. But from 4/3 onwards, B starts moving faster. So much so that by the time you come to 2 seconds, B has caught up with A. Okay, understood this now?
Yes, sir.
Okay. Okay, let's come to some of the parts of question 4. Question 3, you can just go through the solution I've sent. You have to just manually put the values of x as -1, 0, etc., and calculate the value of y from the function, then plot the approximate graph, and rate of change is very easy. You have to just differentiate it. Okay, so I think the explanation I've sent in the hints will be enough. Question 4, there are some tricky parts. Let's work them out. So before I come to the E part, let's look at, for example, D part. So this is a type of thing that looks very complicated, but we have to basically just simplify it, and then it becomes easier. So x cube into root x, is it? No, sorry, x square into root x minus x cube, the whole thing divided by 2x. So we want to find out dy by dx. So what we'll do here is first we'll simplify this. This implies that y can be simplified as, first step we can use this operation, okay, and then next we can express it as okay. So this will become power 3/2, and this will be okay like this. So once you've expressed y like this, it's much easier to differentiate this. So next you can take the differential operator inside the bracket and complete the differentiation part. Okay. So hope this is clear. Just make a quick note of this if required.
Sir, sir, I had a doubt in question 4C part also.
Okay, so just complete this. So this will become 1 by 2 taking the constant outside, differentiation of x to the power 3 by 2, minus again take the constant 1 by 2 outside, differentiation of x square. So that is so 3 by 4 root x minus x. This should become the derivative or the differentiation. Okay, let's also look at the E part.
Sir,
Yes.
I had a doubt in the C part because like the solution which you had sent, and in the doubt lecture also this question had been asked. So there the sir had done it in a different way.
In the doubt lecture,
In the doubt lecture, we had asked this doubt about this y square is equal to x raised to 6 minus 6x cube plus 9. So there sir just directly differentiated both sides, and in the left hand side he applied chain rule.
so see, chain rule, why I have not taught, I have not given in the solution is because I have not taught you chain rule yet. Okay. But in the C part, the first thing is actually the way the function is, way the expression is given. It's not a function.
It's not a
You know, so that is the first point. Okay. So technically we can say that we cannot differentiate it only because it's not a function.
Yeah.
Okay. But we can interpret it in such a way that out of that given expression, there are two possible functions. And based on those two possible functions, there are two different values of derivative that we can get. And that is what I have sent you in the hint and solutions. Okay.
Okay.
So we have got this expression that y square is equal to x to the power 6 minus, what was it? 6x cube, no? Yeah. Minus 6x cube plus 9. Okay. Now, of course, we can apply chain rule and all that, but since I have not taught you chain rule yet, so I won't apply that over here. But what you can notice is that the right hand side is a whole square. So express it as a whole square first. It is x cube minus 3's whole square. So this basically means that y is equal to plus or minus of x cube minus 3. Okay. So that means it is first of all not a function. Okay. But out of this, we can generate two possible functions. If we say y is equal to x cube minus 3, then we have a possible derivative. And on the other hand, if we say y is equal to 3 minus x cube, because it's minus of x cube minus 3, then we have another answer. Okay. So if this is the case, then our answer for dy by dx, as you can see, by differentiating this, we'll get 3x square. Or if it is this, then the derivative is minus 3x square. Okay. So at this stage, based on the knowledge that I've given you about differentiation, this is the final answer we should give, that if this is the expression given, it is basically not a function. But if we want to convert it to a function, we have these two options. And for each of these options, we have different value of derivative.
Okay, sir.
Is it clear now? No? Okay.
So,
Yes.
sir, if an equation is not a function, we cannot differentiate it.
No, we have to convert it to a function and differentiate it. You know, basically what it means is like, for example, if I have the equation y square is equal to x, now, so y is equal to plus minus root x. Okay. Now, if you look at it geometrically, what this means is that if I look at the graph of y is equal to root x, that will be a graph like this. And if I look at the graph of y is equal to minus root x, that will be a graph like this. So individually, we can differentiate these terms. We can differentiate y is equal to root x. We can differentiate y is equal to minus root x. Okay. So for example, if I have this point on the graph, x is equal to 1, y is equal to 1, this point 1 comma 1, and I want to draw tangent at this point and find the slope of the tangent, then this slope will be equal to basically what? It will be equal to the derivative of this function, the above one, that is root x, its value at x equal to 1. Okay. So differentiation of root x is what? 1 by 2 root x, its value at x equal to 1. So that is 1 by 2. But on the other hand, let's say I want to find the slope of the tangent at this point. So this one is having a y coordinate of -1. I want to draw this tangent and find its slope. So then for this, what I have to do is I have to find dy by dx for y equal to minus root x, and then find its value at x equal to 1. So when I do that, that slope will come out to be equal to -half. So this tangent is having a slope of -half. This one on top is having a slope of +half. Okay. So as far as finding the slope of the tangent is concerned from the graph, we can do that. But for that, we have to actually first split this and express this into two functions. Then we know that, okay, which function we are dealing with for which particular point.
Okay, sir.
Understood now? So yeah.
Yes.
Okay, so let me clarify the E part also, because I think there is an error in the hint or solution that I have sent you in the E part. So please just make an additional note of the answer which I'm going to get over here. So root x into x square plus 5x plus 2. So to find dy by dx, okay, what I can do here is I can first simplify this. Sorry, before dy by dx, what I can do is I can simplify this as x square into root x plus 5x into root x plus 2 into root x. So further this will become x to the power 5 by 2 plus 5x to the power 3 by 2 plus 2x to the power half. So now I can differentiate it more easily according to the principles that we have learned already. So we can see so unfortunately in the hints part which I sent you, I think I missed out this 2. So there's an error in the answer. Okay, just make a correction for that. So this will become 5 by 2 x to the power 3 by 2 plus 5 into 3 by 2 x to the power half plus 2 into half x to the power minus half. So the final answer should be this. Okay. Or you can further simplify it. Okay. So if you take LCM, you can express this as x square plus 5x square plus 15x plus 2. So I think in my answer key, this 2 is missing. Okay. So just make a correction. Okay, just going through your text messages again. Parth, you have asked me about the derivation of this formula. Okay. This we will learn the derivation at a slightly later stage because it involves something called binomial theorem. Okay. So this derivation, it involves this step that we have to solve this limit delta x tending to 0 of x plus delta x to the power n minus x to the power n upon delta x. So to solve this, we will apply something called binomial approximation method. Okay. Which we will learn as part of binomial theorem in maths. Okay, and when we do that, we'll come back to the derivation of this. So at the moment, you just understand this as a formula that comes from a pattern, that if you differentiate x square using this method, you can show that it is 2x. If you differentiate x cube by this method, you can show that it is 3x square. So it follows this pattern, that it is nx to the power n minus 1.
Sir,
Yes.
sir, I had a doubt that the answer you got for that 4e, the last answer, it can be further differentiated. So the answer we get at the end, will it not stand true for the question?
Sorry, which one? This part 4e.
Yes, sir.
This is the answer only, no? This one.
Yes, sir, but it can be further differentiated, no?
But why I want to further differentiate? This is only the derivative, no? Differentiation step is done over here only, no, beta?
Okay, sir. Thank you.
Got it, no? Further differentiation is a different thing, no? That is called second derivative. Again, that is not something that we have learned yet. But here I want to find the derivative only, no? Only the differentiation, not the second derivative, right?
Okay, sir.
Okay. Anyone has a doubt in the fifth question?
Can you scroll up for 1 minute?
Yeah. Okay, done with this? Okay, so I'll briefly explain the fifth question. So in question 5, there is some information given to us indirectly about the function y. Okay, y is a polynomial function. of x, but such that now this all information is given that derivative of y or differentiation is a quadratic function. Okay. So if this is a quadratic function, what does it imply? It implies that y, that must be a cubic function. Okay. Because when we differentiate x to the power n, the power becomes one less. No? So an x square term I'll get by differentiating an x cube term. An x type of term I'll get by differentiating an x square type of term. And a constant I will get by differentiating a linear type of term. So this must be cubic. This must be of the type, let's say, px cube plus qx square plus rx plus s, let's say. Okay. So if you differentiate this, you can see you will get this type of term. So this only is expressed as ax square plus bx plus c. So if the coefficients of x cube, x square and x are like this, then correspondingly in the derivative or in the differentiation, the coefficients of x square being a, the coefficient of x being p, and the constant term being c, they are these. Now additionally, see what is given to us, that y is equal to 0 for x equal to 0, y is equal to 6 at x equal to 1, and y is equal to 0 again at x equal to -1, and also given that derivative is equal to 2 at x equal to 0. So these four pieces of information we have to fit into these equations to get the four unknown quantities p, q, r, and s. So if we interpret this term as equation 1, okay, and the derivative as equation 2, okay, so we can fit this in equation 1 and see what we'll get. Put x as 0, so y should be 0, so that means s should be 0. Okay, put this also in equation 1, y should be 6 when x is equal to 1, so that means p plus q plus r is equal to 6. S is already 0. And put this also in the first equation. So y should be 0 when x is -1. So this is minus p plus q minus r. And this one is about rate of change. So we substitute this in the second equation, which is about rate of change. So dy by dx should be 2 when on the other side x is 0. So we get this third relation. So we can see that s is equal to 0, r is equal to 2. Okay. Now we have p plus q plus r is equal to 6. That means p plus q is becoming 4. And we have minus p plus q minus r is equal to 0. That means minus p plus q is equal to 2. So solve these and you will get q as 3 and we'll get p as 1. So that means y is equal to x cube plus 3x square plus 2x, okay, and dy by dx is 3x square plus 6x plus 2. So from this a is equal to 3, b is equal to 6, and c is equal to 2. So these are the final solutions that we get. Okay, so these are some of the homework questions or assignment questions discussed, and with this bit of revision of what we've learned in differentiation so far. Now, next up, let's move ahead and learn the remaining formulae and properties of differentiation. Oh yes, before we go into more formulae, just a couple of things about terminology that I want to explain. For a given function y is equal to fx, the instantaneous rate of change is given by differentiating fx. Now in short form, we express this as f prime x. So this is a shorthand notation. And this term that we get, it is called the derivative of the function fx. And the meaning of derivative is that it is instantaneous rate of change. Okay, so this is just another name for the term differentiation.
Sir, can you repeat the statement again?
The differentiation of the function fx is given by the short form symbol f prime x, and that f prime x is called the derivative of the function fx. Okay, just written down what I've said. Okay, so for example, if I ask you what is the derivative of, let's say, 3x cube. So the derivative is nothing but this thing, which is this, is nothing but 9x square. So the derivative of 3x cube is this. So this basically means that if the function we are dealing with is 3x cube, then the derivative of the function is nothing but the instantaneous rate of change of 3x cube, which is 9x square. So this one is the derivative of fx. Okay, so it's just another name for instantaneous rate of change, and f prime is just a shorthand symbol for d by dx or differentiation of fx. Now, of course, we might have an application where the variable is different. So for example, if s is a function of time, then ds by dt is the derivative of this function. Okay, so let's come to some additional differentiation formulae. So having seen the differentiation of x to the power n, which is the primary formula for all algebraic functions. Okay. Next, we move on to differentiation for trigonometric functions. Okay, so differentiation of sin x is given by the formula cos x. Differentiation of cos x is given by the formula minus sin x, and differentiation of tan x is given by the formula sec square x. Now, obviously, there is a derivation and a logic for each of these formulae, but at this stage in basic calculus in physics, we will not be interested in the derivation. For us, what is essential is the application of the formulae. The derivation again comes by applying the definition or the basic principle of differentiation along with some trigonometric properties. And you will be doing the derivation later in advanced calculus in mathematics. But here we have to focus on the application part for physics. And for that, for us, what is important is the formulae. Especially the formula of differentiation of sine and cos is going to be very important in future chapters. Then we also have the other three functions.
Sir, it is sec square x.
Yes, sec square x. Okay. So that is like sec x is the inverse of cos x, 1 by cos x. So that one. Sec square x. Okay. Similarly, differentiation of cosec x. But you know cosec x is 1 by sin x. That is given by the formula minus cosec x cot x. Differentiation of sec x is given by the formula sec x into tan x. And differentiation of cot x is given by the formula minus cosec square x.
Sir,
Yes.
Is there
Sir, is
derivation
there-
for it?
Okay, let's go one at a time. Yeah, Priyam, you are asking some question?
No, sir, I was asking a question.
Yeah, okay, Vineet.
Sir, is there like a derivation for it?
Yes, I told you that there is a derivation of this from the basic principle, but that derivation you will be looking at in advanced calculus in maths. Okay. At this
Okay, sir.
stage over here, we will not be looking at the derivation of it because it's not important for us. Okay.
Okay, sir.
Sir, so is there any logic or something that we have to remember the formulas from, or we just have to learn them for as of now?
You just have to learn them bit as of now. Okay.
Okay.
Just have to learn them and you have to learn how to apply the formula. That is the more important thing. Okay. Do you know the formula of sin A plus B? Sin A cos B plus cos A sin B?
Yes.
Yes.
Okay. So that is one of the things that is used in the derivation of this sort of formula. Okay.
Sir, so can we write
Yes.
d by dx sin x as sin prime x?
Sorry, come again, Darsh. Can you speak a bit louder?
Can we write d by dx sin x as sin prime x?
Yeah, you can write it as sin prime x. Okay. But generally that prime notation we use for the function, not the value of the function.
Okay.
If you're writing it in prime notation, it's better you write it this way, that sin x's prime is cos x.
Okay.
Okay, so let us look at the interpretation of a couple of this as an example. Okay, so for example, if we plot the graph of y equal to sin x from x equal to 0 to pi, okay, and find the slope of tangent at x equal to, let us say, pi by 3 or 60 degrees, and x equal to, let us say, 3 pi by 4 or 135 degrees. So let's see how we can apply the differentiation formula for doing something like this. So the first part, the graph plotting, that comes from our basic knowledge of trigonometry. So that is not really anything to do directly with differentiation. So the graph of sin x from 0 to pi, it will look something like this. From 0 to pi by 2, it will first increase from 0 to 1. And then from pi by 2 to pi, it will again decrease. So some sort of shape like this we will get. Where, for example, we can see that at pi by 3, sorry, at pi by 6, which is 30 degrees, the value is half. At pi by 4, which is 45 degrees, the value is approximately 0.7. But then that value repeats again at 5 pi by 6. This value again repeats at 3 pi by 4. So that is as far as the graph is concerned. Now we want to do this. We want to find the slope of the tangent at pi by 3. So that means what we want to do is, let's say this point is pi by 3. So at this point here, we want to draw a tangent line. And we want to find its slope. So if y is equal to sin x, we know the instantaneous rate of change will be the derivative of sin x, which we know from the formula above is cos x. Therefore, at x equal to pi by 3, the slope of the tangent equals to cos pi by 3, which is cos 60 or half. So this tells us that the slope of tangent will be equal to 0.5. So this line that we've drawn, its slope is equal to 0.5. You can see it's having a positive slope from the shape of the graph. Whereas next, when we draw the tangent at the point 3 pi by 4, so that means at this point we are drawing a tangent. So what we expect is we should get a negative slope. Okay, so just note this down and try the B part yourself. How much should be the slope at x equal to 135 degrees or 3 pi by 4?
Sir,
Yes.
after in the solution A at pi equal to pi by 3, 60 degree, dy by dx equal to, is that cos pi by 3?
Yes, that's cos pi by 3 because dy by dx's value is cos x, no? So when
Yes.
we substitute the point, we have to replace x with pi by 3.
Okay, sir.
So it becomes cos of pi by 3. So we have to basically substitute this with x equal to pi by 3. Okay, very good. That's correct. Manav, Parth, Yug, Jitendra. Yes, Parth, that's correct. Shreyas, correct. Shaurya, correct. So B part, we want to find the slope of the tangent at x equal to 3 pi by 4. Okay, so we know that dy by dx is equal to cos x. Therefore, the slope at x equal to 3 pi by 4 is the value of dy by dx at x equal to 3 pi by 4. So that will become cos of 3 pi by 4. Now for cos of any theta which is obtuse, we have the formula is minus cos of pi minus theta or minus cos of 180 minus theta. So cos of 3 pi by 4 will be expressed as minus cos pi by 4, or cos of 135 degrees will be expressed as minus cos 45 degrees, which is minus 1 by root 2, or approximately minus 0.7. So this one will have a slope of negative of 0.7. And you can see that in the graph, the slope is negative. Okay, so this is how we apply the differentiation operator to find the slope of the tangent at a given point in case of something like a trigonometric function like sin x over here. This is the graph of sin x. And we are using the derivative of sin x, which is cos x, to find the slope of the tangent at two different points like this. Okay, let's do another quick question. For the graph of y equal to tan x, find the slope of the tangent at the point x equal to pi by 4 or 45 degrees. Just try this out, people. Yes, very good. A lot of people have got the correct answer. Sambhavi, Tanish, Tavish, Tanay, Parth, Jitesh, Arya, Parv. The correct answer is 2. Okay. Ishfaq, correct. So let's see the steps involved. So the derivative of the function. Now this is directly from the formula that we are seeing. It is sec square x. Okay. So therefore, slope at x equal to pi by 4 becomes the value of the derivative at x equal to pi by 4. So that is sec square pi by 4. Okay. Now sec x is 1 by cos x. Okay. So therefore, sec pi by 4 is 1 by cos pi by 4, which is 1 upon 1 by root 2. So that is root 2. Okay. So this becomes root 2 square, which is 2. Okay, so that is the slope of the tangent at x equal to pi by 4. So in your trigonometry lessons in maths, you might have seen the graph of tan x. It's a somewhat more complicated graph compared to sine and cos. So that graph kind of goes from 0 and approaches infinity as x approaches pi by 2. And then again, second quadrant, it goes from minus infinity to 0. And third quadrant, again, it goes from 0 to infinity. And this is how the graph progresses. Okay. So our pi by 4 point is somewhere here. So if we draw a tangent at this point, it should be a straight line like this. So this line has a slope equal to 2. This is what we interpret this instantaneous rate of change at the point x equal to pi by 4 as. Okay, so this is about the trigonometric functions. Now let's come to two more essential formulae for two more essential type of functions. So next we will look at the exponential function. Now this function is a very unique function in maths and physics. It has a very important and unique property. So first of all, let us understand what is the exponential function. It is given by the formula y is equal to e raised power x, where e is a constant. E's approximate value is 2.7, but e is actually an irrational number like pi. So it is a number which has non-terminating or non-recurring decimal. But if we approximate it up to first place of decimal, it is 2.7. And the graph of the function e raised power x, therefore, looks like the following. It looks like a curve like this. So for example, you can see that at x equal to 0, the value of y becomes 1, which I have shown in the graph. Okay. At x equal to e, for example, x equal to 1, for example, the value of y will be e, or approximately 2.7. But at x equal to 100, for example, the value of y will be e raised power 100, which is very large. Okay. So at x tending to infinity, y will tend to infinity. So that is what justifies how this graph increases. So it's increasing very rapidly on this side. Whereas if you look at it on the negative side, it decreases. Okay. So that is the nature of this graph. Now, what is unique about this function is that the derivative of the exponential function is given by the following formula. Okay, so this is the unique property. The value of the derivative equals to the value of the function. Okay, so this is about the exponential function. And finally, the last of the functions that we'll be studying is the natural log function. So the symbol we use for natural log is ln. So the term ln stands for natural log of x. And what it means is that it is log x to the base e. where e is that exponential number. So the graph of this function now looks like this. So first of all, we cannot define y for non-positive values of x. Okay, now the derivative of natural log function this is given by the formula 1 by x.
Sir,
Yes.
sir, can you please explain where will the function be undefined?
The function will be undefined for example, for any value of x less than equal to 0, y cannot be defined. You
Yes.
understanding the point now? Because see, y is equal to ln x. This implies that x is equal to e raised per y. Okay. So the thing is, from this expression, you can see na, that
Yes, sir, that.
You cannot define y for a non-positive value of x.
Yes, sir. Understood.
So basically, like for example, if x is equal to e raised power minus 1000, which is almost tending to 0, because this is 1 by e raised power 1000. Okay. Y's value is how much? It is minus 1000. So if x is tending to 0, y tends to minus infinity, which you can see on this. Okay, but at x equal to 0, y is undefined, and again at x negative value, y is undefined. So that is the nature of the logarithmic function. Okay. Another general thing you should know, that in logarithms in general in maths, for log, the standard base is 10. So when we use the expression log of some number, it basically means log of that number to the base 10. So for example, log of 1000 will be 3, because 1000 is equal to 10 raised by 3. So that's the standard base. Whereas the natural log base, as we've just seen, is e. So ln x is log to the base e of x. Now, we can also have any arbitrary base. Okay. So for example, log of 16 to the base 2 is how much? It is 4, because 16 is equal to 2 to the power 4. Okay. But the formula that we've got for differentiation, that applies only to natural log. It doesn't apply to log of any other base. This formula that we've got, it is only for natural log, that is log to the base e. We cannot apply this to log to the base 10 or log to the base some other value. Okay, so now based on all the new formulae we have learned, we can easily differentiate simple combinations of these formulae. So for example, we have something like this. Y is equal to 2 sin x plus cos x. And we want to find dy by dx and slope of tangent, let's say at x equal to pi by 6. So all we have to do is use the formula of sine and cos as differentiation or derivative, and then substitute the value as pi by 6 for the slope of the tangent. So here, for example, it will become differentiation of 2 sin x plus cos x. So for this, we'll use the same properties that we'd seen earlier for algebraic functions. Differentiation of the first term, that is differentiation of 2 sin x, the 2 comes outside, plus differentiation of the second term, which is cos x. Now we use the formula. We know that differentiation of sin x is cos x and differentiation of cos x is minus sin x. So this becomes the derivative of the given function. Okay. And from this we can see that slope of the tangent at x equal to pi by 6 will just become the value of this function at pi by 6. So that is 2 cos pi by 6 minus sin pi by 6. So that is 2 into root 3 by 2 minus half. So that's root 3 minus 1. So root 3 minus 0.5. So we can write it approximately as 1.73 minus 0.5. Or 1.23. Okay, so these all type of functions we can deal with quite easily. Okay. But on the other hand, we can also have functions which are combination of the various types of functions that we've studied. For example, if we have a function of this type, x square plus sine x, okay, then to find the instantaneous rate of change of this, we have to use a combination of the two types of formulae. Differentiation of algebraic function using the x to the power n rule, and differentiation of trigonometric function using the other formulae. So this will become 2x plus cos x. Okay. But then what if we have an example like this? Y is equal to x square into sine x. Okay. Then we have to use some other property. Okay, this is the product of two functions, x square and sine x, which are different type of functions. So we can't simplify this further and use the earlier properties. So for this type of function, we have to use another property. So for this, there is something called a product rule. For differentiation. Okay. So having done the formula, let's look at additional properties of differentiation. Okay. So for example, already we have seen a couple of the properties that differentiation of a constant is 0. Differentiation of a constant multiplied by a function, this is also a property. Okay. Now like this, today let's learn a new property which is called the product rule for differentiation under properties. So if the function itself of y is actually the product of two functions, So for example, y is equal to x square sine x. So we can say that fx is x square and gx is sine x. So y is the product of these two functions. So then the derivative of this function or derivative of y with respect to x is given by this formula. Differentiation of the first function into the second function plus first function into differentiation of the second one.
So,
Yes.
sir, likewise, if a function is a product of three functions, we will have to apply this rule twice, right?
Yes, we will have to apply this rule in a sort of cascaded form. So we can like bracket two of the functions first, okay, and apply it to that particular bracket and then apply it to the third one.
Sir,
Yes.
so can we say that if a function is a product of n functions, then the number of times we have to apply the product rule would be n minus 1?
Yes.
Okay.
There'll be n minus 1 terms, you can say, when we open this.
Yes.
Sir, can you show an example where three functions are used?
Yeah, I mean, for example, we could have this only, no? Could have a function like y is equal to x into sine x into cos x, for example. Of course, this you can simplify by writing this as sine 2x by 2, but we can treat it like the product of two functions, three functions, okay? Or we could have totally different type of functions like exponential function into algebraic function into trigonometric function. These are examples of three. So when we differentiate such a function, what we'll do is first we'll take these two as a single function and this as a single function and apply this product rule. And for the product rule, when we are differentiating this one next, we'll again apply product rule inside the bracket. So basically we'll get three terms then. Derivative of first function into second into third, then first into derivative of second into third, then first and second multiplied by derivative of third. Okay, but let's like keep it simple in the beginning. Let's first look at the application for some simple two function products. Okay, so y is equal to x square sine x. You want to find the derivative of this function. So let's just apply this principle here. So dy by dx will become f prime x, which is differentiation of x square into gx, which is sine x, okay, plus f, which is x square, into differentiation of the second one, which is derivative of sine x. So this, as you can see, will become 2x sine x, plus this will become x square into cos x. So this becomes the derivative of the function. Okay, so hope this is clear. Try out another example. Okay, just quickly work this out. This shouldn't take time at all. Yes, Parv, that's correct. Jinendra, correct. Sambhavi, correct. Manav, correct. Okay, so let's check out the values. Yes, Darsh, Tanay, correct. Jitendra Tiwari, correct. So let's start with the differentiation. It is the differentiation of two very simple functions, x and e raised power x. So differentiation of x into e raised power x plus x into differentiation of e raised power x. So that becomes e raised power x plus x into e raised power x, or we can write it as 1 plus x into e raised power x. So that is the derivative of the function. So the slope of the tangent will be the value of the derivative at, in this case, x equal to 1. Okay, so 2e is enough for the answer. Okay, we can just leave the answer as 2e itself. Or we can take the approximate value of e as 2.7 and get the numerical answer as 5.4. So these are examples of the product rule. Okay. Now, similarly, another rule we have in differentiation is the quotient rule. Okay, so this is when the overall function is defined as the quotient or division of two functions. Okay. So for example, we have y is equal to e raised power x upon sine x. Of course, we can also write this as e raised power x into cosec x, but my whole point is, okay, or if we have the inverse of this, that y is equal to, let us say, x square upon e raised power x. Something like this. You can see it's the quotient of two functions. Okay. So then this derivative is given as denominator into differentiation of numerator minus numerator into differentiation of denominator divided by the denominator whole square. So it's a bit of a lengthy and complicated formula. In shorthand notation, we can write it like this, that if y is some numerator divided by denominator, then dy by dx is denominator into derivative of numerator minus numerator into derivative of denominator divided by square of the denominator. This is the shorthand notation. Now, one very interesting example you can see of this is that just a while back we had seen that differentiation of tan x was sec square x, but we can also interpret this like this, that if y is equal to sin x by cos x, that's the same thing as saying that y is equal to tan x. But expressing it like this, we can write it by using this formula, and you can show that that's how you can find out the differentiation of tan x using sin and cos. Okay, so if you use this quotient in the formula above, you can see it is cos x into differentiation of sin x minus sin x into differentiation of cos x divided by cos x whole square. So this will become cos x into cos x minus sin x into minus sin x divided by cos square x, which will give us the identity cos square x plus sin square x in the numerator, which you all know is unity. So 1 by cos square x, which is sec square x. We try out another example. Okay, so let's quickly look at the answer of this. Yes, Manav, that's correct. Perf, again, that's correct. So differentiation will be denominator into differentiation of numerator minus numerator into differentiation of denominator divided by the denominator whole square. Something like this. Okay, people. So I'll just take another 5 minutes extra because unfortunately I had to delay the start today because of network issues. We'll just complete in another 5 minutes. I want to discuss another property of differentiation, the last one called chain rule. So chain rule is the method of differentiation of what we call composite functions. Let's understand what is a composite function. Composite functions are of the type a function of a function. This is a composite function. For example, I have y is equal to square root of 1 plus x square. This is a function of a function, okay? Because I can say that gx is equal to 1 plus x square and f of gx is equal to square root of gx. So this is an example of a composite function. So to differentiate composite functions, we apply chain rule. So chain rule involves 3 steps. So it's very important you understand these properly. So the first step is called the substitution step. Wherein we introduce a dummy variable. Okay. So say let z is g of x. So this is our dummy variable. So y becomes f of z. Okay, just make a quick note down up to this step. Then we'll see the second one, which is the chain rule step to differentiate. Okay, so next step, once we have established the dummy variable, then comes the differentiation step, which is the chain rule application. So we express the differentiation of y with respect to x as the differentiation of y with respect to the dummy variable z multiplied by differentiation of z with respect to x. So this becomes, as you can see from here, this becomes f prime z into g prime x. And the final step before we write the answer will become what we call resubstitution. That is, we resubstitute the value of z as gx. Okay, here. So that we get the final answer. That completes this. Okay. So note down these three steps and let's understand them in the context of our example. Y is equal to square root of 1 plus x square. We'll apply these steps over here. Just a moment. Okay, so let's correlate from here and see how we apply the steps. So step 1, when we substitute, we'll introduce z as 1 plus x square. So this is the dummy variable. So accordingly, y becomes how much? Y becomes square root of z. Then the second step, the application of chain rule. So dy by dx should be dy by dz into dz by dx. So that is differentiation of root z multiplied by differentiation of 1 plus x square. So that is 1 by 2 root z into 2x or x by root z. And then that brings us to our final step, which is the resubstitution step. So z will be resubstituted as 1 plus x square. So dy by dx will become x upon root z, which is x upon square root of 1 plus x square. This becomes our final answer. Okay. So these type of functions, the moment you recognize that in your function you have two operations, one on top of the other. So the function x is first operated with a function g to get gx. And then on gx, we operate another function from top, which is f. So we get f of gx. So the moment you see you have a function of that type, which is called the composite function, you have to use this substitution step to first simplify the function as y is f of z, where z is g of x, and then use the chain rule like this. Okay, people, so hope this is clear. So with this, we have learned all the basic techniques of differentiation, the properties and the various formulae. So with some practice and with all these tools, we are in a position to differentiate any type of function given to us, especially at the physics level. Okay. So we will conclude today's session here. Next time, we will look at some more practice examples of the application of these. And then we will also look at the applications of differentiation itself. Like apart from finding the rate of change or the slope of the tangent, what else we can use differentiation for? Okay. What other properties of a function like maxima, minima, etc. it gives us. So we will learn that in the next coming lectures. So please go through today's session notes very carefully. And I'll also be sending you a worksheet to solve along with it. Okay. So that's it for today's session. People, wish you all the best and thanks for
Thank you,
attending.
sir. Bye, sir.
Okay, people. Bye.
Bye,
Bye,
sir.
sir.
Bye, sir.
Bye, sir. Thank you, sir.
Bye, people.
Sir, we can submit the homework. We should submit the homework on Discord, right? After
Yes, yes, you can submit it. No, there is a page
Ah.
for homework submissions on you know on your Blue House link, right? You can submit it there also.
Okay.
Okay.
Sir,
Yes, yes, I have.
sir, in the product rule example, 2x, the derivative was 2x something, 2x into sine x. So, sir, x will be in form of constant or degrees there for finding
No.
the slope then?
X is the variable, na beta?
Yes, sir.
So for example, we had the function x square into sine x, na? Right?
Yes, sir.
तो उसका डेरिवेटिव कितना आया था 2x sin x plus x square cos x, right?
Yes, sir. Yes.
So suppose I want to find the slope of the tangent at, let's say, 30 degrees. So I will substitute 30, but in SI unit, that is pi by 6. So I'll substitute the value of x as pi by 6. Okay, na?
Okay, sir.
So how much will the
pi
slope
by
become?
6.
So it will become pi by 3 into half, you know, because that is 2x sin x. Okay.
Yes, sir.
Plus x square into cos x. So that will be pi by 6 ka whole square into cos pi by 3, which is, or cos pi by 6, which is root 3 by 2.
Okay, sir.
So I'll get the answer in terms of pi only, na, then. But that is the SI
Okay.
unit. Okay.
Yes, sir. Okay.
Okay.
Thank you, sir. Bye, sir.
Okay. Okay.
So, and from the modules, which exercises can we start doing?
You can start with the exercise 1. In fact, in today's assignment, along with that, I will send you a list of questions you can do also.
Okay.
So there is a couple of in-chapter exercises you can do. Okay. I'll specify the page numbers, and exercise 1, the questions in section 1, 2, and 3 you can do completely, plus some selected questions of exercise 2, 3, and 4 also. So I'll be sending that to you. Okay.
Sir, actually, I was actually bored, so I did exercise 3, the application of derivatives one.
Okay, you have done very good. You
Yeah,
can
so
send me
let's
some of the solutions if you like. Okay.
Okay, sir.
You can go through them.
Okay, sir.
Okay.
Bye, sir.
Okay. Okay.